my browser window for starters.
Okay. Okay, welcome everybody. People from Edinburgh, people from China, people from outside of the company. Welcome to this technical talk. It is my great pleasure to introduce my friend and collaborator, Jamie Gabbay. Jamie is very well known for his pioneering of what's now called nominal techniques, which is a mathematically elegant and very useful treatment of this very interesting data type that we use in computer science a lot, which is called names. And before his work with Andy Pitts at Cambridge during his PhD, it was maybe neglected a little bit. And he introduced a lot of order in this area of mathematics, computer science, and logic. He wrote a lot of interesting papers. His contribution was recognized recently by the very prestigious Alonzo Church Prize, along with Andy Pitts. And I think some other prizes. I apologize if I don't remember all the prizes that you were awarded for this your very influential work. The work is of a theoretical and foundational nature, but there have also been implementation of it. For example, Nominal Isabel, which is it's a variant of the Isabel detector, which uses nominal data types, and also more recently, Jamie has implemented nominal data types in the programming language Haskell, which is now a package of Haskell. And as you will see, it has quite a lot of interesting applications, making certain kinds of data more easier to express and to reason about. So without going on and on for too long, I'll just pass the attention, the focus to Jamie. So here you go, Jamie. Thank you very much for coming.
Dan, thank you very much for that wonderful introduction. Thank you all very much for coming. It's been quite a year. I hope you, your family, and your colleagues are all well. And I just want you to know that I am here for an hour for you. So please do not hesitate to ask questions, interrupt. Possibly unwisely, I'm doing this talk with live coding and free flow discourse, which makes me particularly dependent on your participation to guide me. So if you see something and you want to know about it, then just ask, right? That's very much encouraged. And this applies to all of you, the ones with the video feeds and the ones without. And as discussed, feel free to put your hands up. I will ask you to do so for some interaction. We've already practiced raising hands, so let's just talk a little bit about this package, which you should be able to see on the screen. Yep, here it is. So it's here. This is it, and anyone can just download this package and use it. And it's a package. It's not a new programming language. It's a thing that lives inside Haskell and can just be used like any other module. Little sanity check, please. Could I have a show of hands? Who has heard of Haskell? Hands up, please. Thank you. That's a good show of hands. Hands down, please. Now, just out of interest, has anybody here not heard of Haskell? I'm seeing no hands. Okay, so I'll assume that everyone here knows what functional programming is. You might not be able to fire up the Haskell compiler, but you can fire up a compiler that's like Haskell. So the code also lives on, lives on GitHub. So let me just see if I can do the share. How do I do this? Aha. So now I want to share. This, I believe, should do it. Haha, yes. So here's how you get it. If I were to press return now, then it would clone the GitLab repo and you just have the file. You're very welcome to do this right now if you like, so that you can play along with me. Any questions so far? Javier, can you just advise me? Are there any hands anywhere?
No, there are no hands.
That's fine. This is all fine so far. So you know what? I'll just
Jamie, I have a
mention.
question.
Yes, please, Dan. Thank you. That was
Can
quick.
you get it through a package manager like Cabal, or you have to go to Git?
Very good question. Thank you. Yes, it's in Cabal, and it's in Hackage, so that's implicit. When I started, I had the Hackage page open, so it's a registered Haskell package. Thank you. Very good point. I'd also like to mention that I've gone to considerable lengths to document this thing. I don't want this to just be expertware. So here, this is a Hackage package. This is how you can get it directly locally, if you like. And I've written some tutorials, which are here. You can find all of these resources directly from the web pages. And I hope you'll agree, looking at the pages, that I really have tried to explain myself. The world doesn't owe it to me to understand what I'm saying. I have to explain myself to the world, and I've done my best. By the way, if you find something that isn't clear in the documentation or examples, then please just let me know. I want to show you the examples, so let me share again. I will switch to, yeah. So these are the examples. There's a tutorial. Let's just nip into that. I will go through this just to explain how the package works. There's the example of the untyped lambda calculus. So you may or may not be aware, the untyped lambda calculus has this thing called capture avoiding substitution, and one of the basic use cases for this package is to write a really neat and compact evaluation function to weak-head normal form. So that's living in here. And in fact, I will just show you the code just because I can, so you just get a feel of what it looks like. So this, this is evaluation to weak-head normal form. I'll come back to this, but you'll notice, well, it probably looks a bit confusing because you're not familiar with the notation, but it's short and sweet. And that's basically because all of the difficult bits in this example are name handling, and name handling is taken care of by the package, so there's nothing difficult left. Any questions so far? Okay. These two examples are taken from a name binding package by, I think, by Kmet. I hope I've got his name right. So this is for direct comparison with the existing package. This is a style guide. I wrote a style guide for it, so some do's and don'ts. This is systemf. And systemf is interesting because it has names that are labeled by other names, because term variables can mention type variables in their types. So that's why systemf is interesting. And this is a reference implementation of a blockchain, again implemented using this package. So with a bit of luck, I'll just show you a little bit of how the package works, and then I'll take you on a tour of some of the examples. How does that sound to you, Dan and Javier? You okay with that plan? Okay, so let's just get into, I think it is. So I've already cloned
Ask you a
this.
question.
Yes, please. Who's speaking, please?
Sam. I think you know me.
Sam. Yes. Hello, Sam. Hi.
Hi.
I can't see you, but yeah, I'm sure you're there somewhere.
Maybe you. Yeah, that's. Maybe you can see me now. Yeah.
I can. Yes. It's lovely to see you, Sam.
Yeah, I was just wanting to ask a very high-level question. I know that there are various other ways of doing names in languages like Haskell. I was wondering if you could just sort of give a high-level feel of does your approach work more smoothly in some ways or not in other ways? I mean, how does it, at a high level, how does it feel to a programmer, do you think?
How does it fit in? So thank you, Sam. That's a great question. Could you just give me one or two examples of other packages that you have in mind?
Okay, so what I have in mind is that there's lots of ways of encoding, say, untyped lambda calculus in Haskell. You can use the Brown notation, for instance, or higher order abstract syntax and so on. These are things that people routinely implement in GHC, in Haskell.
Yeah.
Does your nominal approach, is it less horrible in some ways, or?
So I definitely say it's less horrible. But
okay.
I'd like
But
to
anyway, sorry, I didn't want to interrupt you. I just wanted to.
It's a good question. This is a segment of the talk that I had prepared, so I'll just drop it in right now. So Sam has said, fine, Jamie, okay, there's this thing called nominal data types package, but hey, there are other things that will manage names. So where does the nominal data types package fit in? There are two ways to answer this. One of them is to basically show you the nominal monad, which is unique. There are even other nominal packages. There's one by Peter Selinger, but I think the nominal monad, which is actually a very simple thing, this does not appear anywhere else. So the short answer to the question, which is a bit reductionist, but still the short answer is I've introduced the concept of the nominal monad. That's one answer. But I want to show you something else, seeing as you ask, just to show the kind of trouble that people can get into without my package, if I may say so. So I want to share with you this. This is from a paper called What is EUTXO Blockchain? And I wrote this, it's been quite a busy year for me. I implemented a Haskell package. I kind of understood what UTXO blockchains are. So just a little history to illustrate an application of this package. A year ago, I tried to understand what a UTXO blockchain is, and I found a lot of descriptions on the web that to me as a mathematician didn't make much sense. They were all kind of hand-wavy and saying, oh, it's a bit like this or a bit like that. And I was like saying, I want the data type definition, please. Where's your data type? And the only paper I found that actually had a data type in it was a paper called the EUTXO model, which I can call up, but it's a bit fiddly doing this with Zoom, so please take my word for it. It's a reference in this paper. That had a data type. Now this is an inductive data type, which doesn't correspond at all visually to what UTXO blockchains look like. So here's a picture. The UTXO blockchain is a chain of blocks, and the blocks have pointers on them. You see this here? And these pointers can join up. So for example here, the right pointer, the output labeled E, has joined up to the input labeled E of TX4. Sam, can you see this? Does this make sense?
Yes.
Thank you. So this is a binding construct. These blocks are manipulated as a bit like PyCalculus processes. These things correspond to channel names, except there's two, well, there's even inputs and outputs. So yes, there are these channel names. And you can think of this as restrict E in TX3 and TX4. Now, it's actually restrict E and restrict F in the pair of TX3 and TX4. That makes sense.
Yep.
Now, if you want to model this, say, in Haskell, you can't do this because there's no native restriction function. So you can't just define a transaction to be a pair of a list of inputs and a list of outputs that are labeled names, because there's no data type of names. And you can't say, well, to join TX3 to TX4, I just put them in a list and hit them with a top level name restriction, E and F. You can't do that. Well, you can now, but you couldn't when I started thinking about this. So what the programmers did was they kind of split. So the inductive data type was identifying this binding with the transaction itself. So actually, the way they do it in the paper is that TX4 contains a copy of TX3 at this point. So this linkage is represented just by literally inlining this creature into this creature. Does that make sense, Sam?
Mm-hmm. Yep.
Dan, Javier, I'm using you as my my litmus test here. Am I making sense to you too?
Yeah.
Yeah, sure.
Yep. Okay. So one half of the ecosystem is using a kind of inlining representation where linkage is represented by literally reproducing the data type in here. The other half, though, the half that actually has to write programs, they just use numerical labels and they have functions to rename as required. So if there's a name clash, if there's an E here and maybe an E somewhere else, and they rename the names, okay? Which will be familiar to you, Sam. But it's worse than that, because these renaming lemmas kill theorem provers. So when they're trying to verify these programs, they use yet another system that carries an explicit naming context around. So to be clear at just how bad the situation is, there are actually 3 representations floating around in this UTXO ecosystem of the same data structure. There's this representation, which is in the heads of the users. There's the inductive data type. That's 4 then. Inductive data type. There's an explicitly named system, and there's essentially a de Bruijn system, all floating around. Now, just imagine, Sam, the representation impedance that's going on between these different representations. I would argue that the nominal data types package is a step towards eliminating this problem completely. You can, and you do, when you want to build this, the representation of this is literally TX3 followed by TX4 with a name restriction on the top by E and F, and that's it. And you don't have to take my word for it because it is in the code and you can look at it right now. All you have to do is go to this web page and click on this file here, and you will find that diagram that I just showed you literally implemented directly in code. Implementation impedance is, representation impedance is 0. Let's just go into the code and I'll see if I can find the relevant definition. What I want is a definition of a chunk. Transaction, context. Because now I'm panicking, I can't find it. Am I being stupid? It's in here somewhere. Here we are. There we are. Sorry about that. There you are. So this is it. This is a nominal monad wrapping a list of transactions. And to my knowledge, you can't do anywhere else. This is the only code base that allows you to write this definition. I'll elaborate on it. Sorry, yes, Sam, please.
I said, great.
Okay.
I guess it would be interesting to sort of see the horrible versions. Well, maybe I don't want to see them now, but I can imagine that the other versions are much more contorted.
Well, they are, but I want to emphasize this. It's not just that the other versions are contorted, but unless you are in the field or speaking to somebody who is doing a PhD on this, you wouldn't even know that the other versions are representing the same thing. It's totally a priori not obvious that some de Bruijn representation in a program corresponds to an inductive data type in a paper and corresponds to the picture I just showed you before. So the goal of the system, the high level goal of the system, is to make that not happen anymore. And the reason I'm going on about this, taking the opportunity of your question to emphasize this, is because people tend to think, oh yes, nominal techniques is about abstract syntax with binding. It's not. In a programming terms, I'd say it's about this thing here, this nominal monad, which can represent much, much, much more than inductively defined syntax, although that is the canonical use case. So I'd urge you, if you're in any doubt, to look at this thing here. This is actually a working, quote, reference blockchain system. It's short and it's sweet and it corresponds to the diagrams. I'll now fire up the compiler and we'll actually look at some code. Sam, thank you for the very excellent question. Any other questions, just bring it on. So let's go into the code. Yeah, so here I am, and I'm just going to do a little bit of setup. So I have a little script here, so I'm just going to do a quick cut and paste to give us a nice prompt. There we are. So I've set some flags. I've asked to print types. So there you are. I hope that's all right. I've given myself a funky prompt just because. So let's do some code. Actually, I don't want to be in here. I want to be in English nominal examples tutorial, just because that gives me some types. Okay, so let's just browse our environment. Here we are. So this is what I've set up. So bear with me on this. First of all, I've declared a type synonym. So my name label is a string, just because. And then I've defined a type, my name, which is name labeled by my name label. So these are string labeled atoms, or string labeled names. Let's just create one now. So I'll call n is equal to fresh name, and I'll let n be labeled by n. There you are. Any questions so far?
No.
Okay. So this is great.
Can you create a different atom with the same label? Would that be allowed?
Let's do it. N primed is equal to fresh name. I don't recommend this just because it might be misleading, but yes, absolutely you can.
So n and n prime are different now.
Now, that's a great question. Let's try. Let's check. But watch this party trick, Dan. You ready? N is also not equal to n. But how can this be? What happened? What am I doing? Well, you see, n isn't a name. N is a name in a binding environment. And what equality does is it unpacks a binding environment of n, and then it unpacks a binding environment of n again, and it compares the two underlying names. So bear with me. I'm just going to, I'll call it Cn for concrete name, which is, okay, let's start again. Let's just, A is equal to fresh name. And instead of this, I'll do it monadically, like that. Oh. Somebody needs to mute themselves, I think. My apologies. There we are. So N is a name wrapped up called binding monad in the non-monad. A is a name, and now I will check whether A is equal to A. That returns true. Now I'm going to create a B, and is A equal to B? So that's the question you thought you were asking. Cool. Thank you very much. And I'm just going to do this a different way now, again, to illustrate how this works. So N is going to be a fresh name labeled N. That's fine. And now A is equal to unknown N. Unknown just take something out of the, oh no, it doesn't. Okay, I'll have to do two. There. So I've unpacked N once, I've unpacked N again, and now I have two concrete names which are distinct. Does anyone have any questions about that? Did I scare anyone by saying that N is not equal to N? Do you understand what just happened there? Could I have a show of hands? Hands up who is not happy with what just happened, please. Mario is not happy. I'm very sorry to have made you unhappy, Mario. Could you unmute your microphone and tell me what's not to be happy about?
I'm wondering how this is implemented, because I can see two ways of setting this up so that a name, so that fresh name A is not equal to fresh name A. Either your implementation of equality for the non-monad is just always returning false, which I don't imagine would be very useful, or there's some use of unsafe I/O going on under the hood.
Yes, so there is indeed. No, that's it. Well, there are other possibilities actually. So one which I considered when designing the package was to treat names as resumable exceptions, which I still quite like. And for the record, I actually think that there's a parallel with algebraic data types. Sam, I'm thinking of you, which we might explore. But setting that aside, the way it's actually implemented, Mario, is using unsafe perform IO. So what actually happens when I do this, so let's just be clear on the types here. Let's look at the types. N is a name in a non-monad. And A and B are naked names. And you can actually see their identification token here. This is the number 9 labeled with the string N, and this is a number 10. And if I create a C, I reckon I'll get an 11. 12, fine, whatever. So in fact, technically what happens when we compare A and B is that we compare 9 and 10. Does that answer your question, Mary?
Yes.
Now, here's what you could then ask. You could ask, fine, Jamie, whatever. So you've got A, B, and C, and secretly they are the numbers 9, 10, and 12. But what if I want to rebind A in A? Let me just show you how it works. Now, I'll explain the type in a minute. I want you to look at what this thing actually is. This is, well, A was labeled by 9. This thing here has found every A in the expression here and bound it. That's what this means. And in binding it, it's renamed it locally to 13. So the magic of this is not so much that you can extract names from a binding context. The magic is that you can put them back in. How do you feel about that, Mario? Okay.
I'm okay with that.
So just to refine what I'm trying to express, The unsafe perform IO part is the easy bit. The difficult bit is doing it in such a way that you can then, having performed this, generated this fresh name, you can then rebind it in the result of your computation so that the result doesn't depend on which fresh name you chose. And this is tied in with the fact that nom is a monad that allows you to apply a function under the binding safely, even though the function may assume that explicit names are being used under the hood, which they are. So here's another example. I have three names floating around, A, B, and C. So I'm going to restrict A and B in A, B, and C. This is not Atom's abstraction, this is a restriction, just to be clear. There you are. So you can see that A and B have been bound, but C, which was under the hood, that was 12, has been left unbound. Let's see if I can do this. No, I don't have it. So here's another example. So let me just do this nicely for you. So I've created a fresh name, right, in a nom environment, and this is a very interesting function. Exit is another way of exiting a nom monad. So we have stripped the local name context from A prime to expose an underlying name A. Then we have restricted A once in a tuple, and then we've restricted it again in the tuple. So from one binding context, we create two binding contexts. So let's see what this returns. Notice here how we have 19 here and 21 here. So that's proof that these are two distinct name binding contexts. I have a feeling I may have lost people. So if you're with me so far, if you're not with me so far, please put up your hands. Okay, and video feed people, do you have any questions? Okay, can I move on then? Hands up if I can.
Sorry, Jamie, can you hear me?
Yes, perfectly. Thank you, Sam.
Okay, yeah. No, I missed exactly what was exit again?
Well, let's have a look at exit. So exit is quite a low-level function. We can talk about S-monad offline. Unnom is probably better. So unnom is a way of going from a non-binding to not a non-binding.
Okay, thanks.
That's all. I should probably explain all of these k-noms. So there's this thing called atom, but the type atom is actually equal to k-nom. The thing called, this S is a parameter which allows you to create different name types. So it's technical. I'm not worried about that right now. Fine. Something else. Let's illustrate unknown. I'm a little concerned. People seem a little quiet, so please feel free to ask questions. So here we've created a fresh name in a non-binder, and now I'm going to ask. Let's just look at name label. This returns the label of an S name. So if the name is labeled by T's, then it will return the T label. So I'm going to apply name label to N. I'll tell you now we'll get a type error, but it's very easy why. It's because N isn't a name, it's a name in a binder. So we need to apply it under the non-monad. So we need to apply it under the non-monad. Now this returns a string, but this string is still inside the non-monad, because that's how monads work. Sam, does that make sense to you?
Yes.
Cool, thank you. And just reassure me, Dan, Javier, Mario, are you okay with that? Cool. So it's very easy to get it out of the non-monad. We just unnom it. And there we have the label of n, which is a. So it's this a here.
So would it be reasonable, Jamie, to sort of view this as being like when you're compiling a programming language, you might have multiple variables that all have the same name. You might have multiple copies of A, but kind of internally you give them all a unique name to distinguish them, and that's more or less what's going on here.
I completely agree, absolutely. The only caveat is that, well, not caveat, that the feature that this package brings is it manages all of the renaming stuff for you under the hood, just using the non-monad.
Right.
So if I have two non-scopes and I join them, then if there's any accidental name clash under the hood of the identifiers of the atoms, then the monadic join will take care of doing the renaming for you. Let's just briefly mention abstraction. So I have A, which is a name, and I can also abstract A in A. There you are. So this is what you'd use to model lambda AA. This is the nominal name abstraction that some of you may be familiar with. And it's different from res. This is the monad. It has a kind of flat top-level binding structure, and everything just goes into that. This is an actual distinct data type called an abstraction. And I can illustrate this another way. Abst AA equals abst AA. This will return true because under the hood we choose a fresh identifier for these two names and then compare the bodies. So it's the same fresh identifier in both cases. Whereas if I do res m a a and compare it with res m a a, that returns false because we unpack this non-monad. We basically go under these two monads sequentially and then compare the bodies. But because we went under them sequentially, different identifiers are given to the two atoms. So Sam, this is what you were talking about, and this is what happens with lambda abstraction in a syntactic sense.
Jamie, what's the type of?
Say again, please.
Can you just inspect the type of abst? I'd like to see it.
Yes, of course.
Okay.
So what you might ask now is, what's this? What's this? What's this swappable type class? And this is where the magic happens. So as you know, Dan, some of the rest of you may know, under the hood, nominal techniques are based on a commutative model of names. So what makes a name, or rather what makes an atom, I should say, because in this terminology, names are atoms with labels. So what makes an atom is that you can swap atoms in complex data structures, like models of an ETUXO blockchain, for example. So this is saying that if we have a swapping on the label of the name and we have a swapping on the body over which we're abstracting, then we can form a nominal atoms abstraction. In fact, everything's swappable. So you can derive swappable for everything, just like everything in Haskell is typable. So it's all of these type class constraints are kind of morally pointless because they can always be satisfied. but you have to tell Haskell that you're relying on this so that it can set up internal representations properly for itself. Does that answer your question, Dan? Dan, does that answer your question?
Yeah.
Thank you. And let's look at the type of res. You see, again, the same set of morally superfluous type class constraints. So morally, restrict takes a list of names and restricts them in a body to give you a nominal restriction. But we still need these type class constraints. And if there's any pain in the package, it's with these type class constraints, basically because Haskell doesn't allow monads to be conditioned on type class constraints. So I have to make some compromises in the underlying engineering to get all of this to fit together. And an implicit, if you like, accomplishment, if you can call it this, in the package is that I found a compromise that worked for smoothly for all of the use cases that I could think of, which are listed as examples. That doesn't mean someone else might come along with a use case that my compromises don't work for. And that's what gives me prickles on the back of my neck. But that's where the package could be improved. But I'm running into limitations of Haskell at this point. It's not entirely down to me. Any questions so far? Okay, so what I'm going to do is I am going to, let's look at some, let's go to the browser. Can you see? Yes, okay, it's updated. So I'd like to look at some examples now. So quick look at the tutorial, see if there's anything else I've basically gone through the tutorial. So this should all now be fairly familiar. All the stuff I was just discussing. We make names, we compare them for equality, we can restrict names, we can bind multiple names. This is the example that I just exhibited, where we take a name and restrict it twice under two different scopes. It sounds simple, but actually this little program guided me in the design of the package. I knew that I needed to get this right. Any design that didn't allow me to write this program was not acceptable. This is norm, and goodness. So this is, what's it do? It takes a primed, which is a name in a binding, unpacks it as a name, and then it takes a primed again and unpacks it as another name, and then returns this, and this will come out as morally restrict A in restrict A, restrict B in AAB. That's how it works. This is the monad. Please stop me, ask me to slow down if you need me to, right? That's fine. This is name abstraction. I've covered that. We've actually covered quite a lot of ground. I haven't mentioned concretion, which is how you get out of abstractions. For nominal experts, this conc is much more powerful than the conc you see in the maths papers. It has a substitution action built in. You can do that. So conc is smart enough to recognize when you're an inductive data type. And if you concrete a untyped lambda term, for example, if you concrete nominal abstract syntax at another piece of syntax, it will just go ahead and do the substitution for you, which is actually amazingly convenient. You never have to write a substitution action because generic programming just takes care of everything for you. And when it works really well, I have to say. And here's swappings. The only thing to notice about swapping, which may not be obvious, is that you can swap in a function as well as a inductive data type. So this is Sam, to return to your previous question. This is something that you just cannot do using de Bruijn indexes. You can't swap A and B in a function. It just doesn't work that way. Does that make sense, Sam?
Yep.
Thank you. And this actually really matters because in the UTXO model, there's this thing called a validator, which is actually a function. So if we were using a non-nominal representation, our development would come to a screeching halt right there because it would say, well, I'm sorry, I don't know how to bind a name in a function. But with this system, we don't even notice it because there's a canonical swapping action on functions. So the non-monad will act on a function type just like anything else. I hope that makes some sense. And there's an inbuilt theory of substitution. Okay, so let's just see how this gets applied to the untyped lambda calculus. We create a type of variables that are string labeled names. We create a type of expressions. An expression is either a variable or an application, or it's a lambda of a variable abstraction. So far, so familiar. You've seen this in 1,000 papers, I'm sure. Let's look at how weak-head normal form is actually implemented. To be clear, the point of this is that we can do what's in the original nominal papers, so there shouldn't be any surprises. And there is a little bit of a surprise that I've written this incredibly compact weak-head normal form function, which, I mean, the way it basically works is generic program means that this is substitution. So this is the bit that does beta reduction right there. And it's a one-liner because generic program just does it. And so we identify a beta reduct and then just reduce it, and that's it. This is so short, it's quite maybe hard to see what's going on. So I unpack it in comments here. So we define an explicit recursion, which when it gets to a lambda, applies the function under the lambda binder. I'll tell you about genapp later. It's just a name for the thing that does the obvious thing of unpacking x primed as a pair of a name and a body and applying f. Oh, that should be f3. Apologies. No. Sorry. This 1 should be 0, this 2 should be 1, and this 3 should be 2. That's a typo. Apologies. And then we apply it here. This is the interesting thing. So given an x primed, we unpack it. Given a v, we unpack it as v primed and a. Var x a. So this should be var x. Yeah, and then we substitute t for v. No, this is all broken. I'm so sorry. I don't think I must have copied this code, but perhaps if you squint, you can see what it should be. This is the usual definition of substitution, which takes a lambda abstraction, does the substitution, and then repackages it. Apologies for my error here. The point is, name capture is taken care of. Right, there's this. This is by construction capture avoiding substitution, and you don't even have to say so. That's just what it is. Any questions before I move on?
Do you have any idea what the costs model here is involved compared, for example, to the cost of renormalization using the Bruijn indices?
So just to say this back to you, you're asking how fast this runs?
No, not how fast this runs, because that could be kind of contingent on various implementation details. But if you think of about like a more abstract cost model in terms of, let's say like something more similar to complexity. Like if you had if you had a reduction model where you say, okay, I have a reasonable notion of reduction and I want to count steps in my reduction.
Sure.
So, in an implementation, you get into garbage collection and cache and other very low-level things that may help or not help. But in terms of an abstract cost model, what do you think? How do you think it compares to normalization of the Bruijn indices?
I'm just going to play stupid just a little bit longer. when you talked about steps, you don't mean rewrite steps in a rewrite sense. You mean some kind of abstract notion of computation steps.
Yeah, like if you had this in an abstract machine, how many steps in that abstract machine?
I'd actually, I don't know, but I'd speculate it's no worse than the de Bruijn approach, because the de Bruijn also has a notion of renaming, because you might have to shift. And when you shift, you have to shift the whole namespace. The name management here is via swappings, and so the argument for the package is that it auto-magically takes care of all the swappings. It's all type-driven and generic. But setting that aside, there are swappings, and they may need to actually swap, but you're only swapping the names you need to rather than the whole namespace. Now, the answer to that is fine, then we just defer these things. So we build up a stack of swappings or shifts or whatever you need, and only apply them just in time when we actually need to. And I'd say that part is comparable. There is a notion of some kind of namespace changing thing. There's a namespace changing widget, which can be deferred in all cases, in both cases. So if you want to optimize it, I reckon it would come out about the same, except possibly swappings may have a slightly more subtle advantage because they've got some really nice algebraic laws that they satisfy. So you might be able to optimize by recognizing, for example, that a bunch of names aren't in the support anymore and can get chucked out. That really does happen. Or recognizing that two identical swappings equals the identity, that kind of thing.
What about the complexity of equality checking? Because I think with the Bruijn indices, because you have things in a canonical form, equality checking is very easy. What about with your approach?
This is I understand why you're asking this, but in the context of programming, it's a red herring.
Okay.
There's no complexity hit to deciding equality of these things. What you are creeping up on is another function that's in the package called unifiability. So there's a concept of when two things are equal up to permuting their names. This is not equality, and it's nothing to do with nominal techniques in particular. If you have two data structures with any kind of identifier in them, whether it's represented as de Bruijn or numbers or atoms, it's reasonable to ask, are these things the same up to permuting the identifiers? And it's well known that the complexity of that, if the data type is not structured, so that some permutations, in a structured data type, you can just follow the structure of the data type. And I actually coded up a generic function that does just that. So you can very efficiently check whether two lambda terms with names are equal up to permutations. Almost no coding is required. You can use unifiable off the shelf. And I emphasize this because you couldn't do this in de Bruijn. You need to recode it each time. But complexity-wise, it's the same. If, however, you have an unstructured type-like set, then the complexity is the complexity of searching the permutation space. And that can get hairy, but then maybe you shouldn't be doing that in a programming language, right? Then it's easy to find. Well, set in Haskell isn't really set, as we know. It's actually a tree. That's a separate conversation. But mathematical sets, that's where the cost blow up is. But that's not relevant to the question you asked.
Okay, thank you.
Thank you for the great question. Any other questions?
So why does unifiability come into deciding alpha equivalence? If that's
it doesn't. Oh God, no, it doesn't. This is exact. Sorry, I wasn't clear. Unifiability does not come into deciding alpha equivalence. That's what I was trying to say. The unifiability exists in the code base, but it's not needed for this example at all. That's why I opened on saying it's a red herring.
Thanks.
I don't know who was speaking there. Does that answer the question?
Yeah, it does. Thanks.
Thank you. So I'll tell you where unifiability would come in. So there's a notion of nominal automaton, also called a slightly infinite automaton. And a slightly infinite automaton is an automaton with names and orbits of these names. So actually, I'll tell you what a slightly infinite automaton is. Actually, it's a non-binding of a name-carrying automaton. So there's a Polish school of nominal techniques that studies slightly infinite sets, and that's exactly what the non-monad does. Except these are actually sets, so they're not ordered, whereas things in Haskell in programming languages tend to be ordered. Now, at this point, you might want to ask, are these two slightly infinite sets equal? And at that point, you need to start counting orbits and taking representations and matching them up to unifiability. So there's a whole other library yet to be written that builds on this to build a nominal automaton package, and that might encounter these issues of unifiability, the complexity issues involved, but that's inherent to the maths.
Am I able to clear?
Sorry, say again, please.
Yeah.
Sorry, I didn't catch the question.
I think that somebody is on mute and he was not making a question. I will mute them.
Okay, thank you. So we've hit the hour, but I'd just like to show you System F, because I don't want you to think this is just about untyped lambda calculus. I've given enough untyped lambda calculus talks in my life. So let's just look at the data structures so you can see how this works. We have, System F has two kinds of variables, term variables and type variables. So here are the term variables, a term. Here we are, sorry. So here we have, apologies. This is a type variable, which is just a name that's labeled by a string, right? And here is a data type of types. Here it is. You'll recognize this. And then the funky thing is that then we build terms, and term label is a pair of a string and a type. So the term name is a atom that's labeled by a string so that we can pretty print it, and a type. So this deals with the lambda A of type alpha. The alpha is living in here. Just reassure me, Dan, Javier, Mario, does that make sense? Can you see that?
Yeah. Okay.
And what's funky about this is that everything I showed you in the previous developments scales to the case where atoms, names are themselves labeled with non-trivial data itself containing names. All of the name renaming and the abstraction and the sub and the comp, all of that stuff, it just happens, it just works. Just show you the source code here. There we are, back. I mean, look at it. Just look. There's nothing to it. What does it say? It says you beta reduce and you beta reduce. Once you get past the concrete syntax, it's just giving you two beta reductions. So once you've set these types up, all of the usual apparatus of name binding just works. And now to conclude, I really want to hammer this point home. It's not just about abstract syntax. It works just as well for a graph structured data containing functions. When I showed you this diagram, these things are carrying data loads that are non-trivial, include functions, specifically validators, and those the machinery just runs smoothly through all of this structure. This example is also relevant because it uses the nom-monad directly rather than via nominal abstraction, as is the case for untyped lambda and system F. So this is a different kind of use of nominal techniques, which you may have not seen before. Okay, I'm at the hour, so I'll stop. I'll go on as long as you'll let me. So ask questions or whatever, that's fine. Thank you very much indeed.
Thank you, Jamie. Please give Jamie a virtual clapping. Okay, well, thank you everybody for turning up, and thank you, Jamie, for a really good talk, very informative. There've been quite a lot of questions and discussions throughout. I don't know if there's any quick final questions to wrap this up, because we're past the hour.
Could I just ask about graphs?
Yes, please do, Sam.
Does this make programming with graphs cleaner? I mean, how does that work out?
Yeah, absolutely. So in a sense, I can answer yes already, because the UTXO example
Is a graph,
right. And I program on the graphs, and I have to say, I mean, though I say so myself, it works out really well. It does work out really well. It just does.
So I guess I'm particularly thinking, well, of kind of Dan's line of work. He's done lots of work with graphs and graph rewriting.
Absolutely.
And so on.
Yes, and we've had
does all that
discussions
pan
on
out?
this.
Right.
So part of the reason of doing the UTXO, I encountered this use of names in the UTXO model by accident. I didn't set out, but imagine my surprise when I was writing a paper on UTXO, on the UTXO model, and there I saw, staring in my face, nominal techniques again come right back at me. And I was very much thinking of Dan and what he's done with graphs when I designed that. So this is a program with a secret message to various communities. So the short answer is yes, but there's another answer, which is I'm a big fan of Andrei Mokov's algebraic graphs package. Sam, just so I know, are you aware of this package?
I have heard of it, yeah.
It's a really nice, it's a nice piece of work. And I contacted him and I asked, could we basically combine algebraic graphs with nominal algebra inside Haskell to build a nominal algebraic graphs package? And the answer, after discussion with him, is clearly yes. The bottleneck here is just our time. It's obvious that this can be done. But what's also interesting is he wants to do it, because when I started showing him how it works, he said, yes, yes, yes. If I'd had nominal restriction on my graphs, there are various things I would have been able to do with my package that I couldn't.
Cool.
Exactly. So the answer is yes, definitely from the point of view of this existing development, but I'm actually quite excited also about what could be done further. Thank you, Sam. Any other questions?
I just wanted to ask a bit more about the graphs. Are they assuming any sort of directedness on the graphs, or can I have a completely undirected graph and it kind of work out okay?
Are you asking about Andrei's package or the UTXO, the graphs implicit in the UTXO model?
I'm possibly asking both, I guess. So about the one you've been using for the UTXO blockchains and this sort of potential, like, hypothetical combination.
It shouldn't be an issue. I don't see why it should be at all. So in this development here that I have up, graph binding is literally just a name restriction of a pair of pointers. One pointing forwards and one pointing back, but the forwards and backs comes from the time structure of the UTXO model. The graph doesn't actually care. Does that make sense, James?
Yeah. Then I guess that leads on to, does this naturally model like hypergraphs where edges can go between multiple, more than two ends.
Absolutely. I don't see any problem with that at all. So just to, I will demonstrate using my fingers. Here we are. So this is what happens in the UTXO system. We have an A here and an A here, and just the way it's set up, when you mention them together, they bind and go under a non-monad. So there's absolutely no reason you couldn't have two A's here and an A here. And if I had a third hand, then I'd put it there and have an A there, and that's absolutely fine. So it's an abstract notion of connectedness. Does that answer your question, James?
Okay, yeah, thanks a lot. Thanks.
Thank you.
Okay, well, let's conclude our meeting here. Thank you, everybody. Thank you, Jamie, and hope to see you around soon.
Yes. Thank you, everyone, for coming. There's a lot of people, so I hope you've enjoyed this. If you have any questions, then just drop me an email afterwards. Thank you all very much, and stay safe.
Take care. Bye-bye.
Thank you. Bye-bye.
Thank you. Bye.
Bye bye. Thank you.
Thank you. Bye.